So the simplest distributed load would be what we call a rectangular distributed load. And that rectangular distributed load has a constant intensity. This book uses the symbol W for the intensity. What would be the units of this intensity? Well, it would be something like how many pounds per foot of length, or how many newtons per meter of length. And on the x-axis would be some length or dimension x. And so often a rectangle goes from 0 to b. B would be the width of the rectangle, and that height represents the magnitude of the intensity. Okay, there's two things we want to be able to do is we take a distributed loading like this and we say, I want to have a simplified system. That is a single point load applied at a particular point, which has the same effect as the distributed load, the same effect of pushing the system down. Let's say that's a beam, it's acting on a beam right here. Downward force, as well as rotational motion, or trying to induce some rotational motion. There's no motion in statics, but it's the tendency to make it want to move down and to move in a rotational motion. That's in statics. And so you could say that it would be a magnitude here for the resultant simplified force. And probably most of you would say if the distributed load was uniform over the length from 0 to b, I think that the proper location to put that point load would be b over 2. Right in the middle, right? Okay, so the notation used in the book would be this f of r is the magnitude, and x bar is the proper location of that point load. So, two questions. How do I get the equation for f of r? And then how do I get the equation for x bar? So we look at it and we say, what exactly is this W? I try to every now and then slip and call it omega. Sorry. It's just W in this textbook. It's our intensity, which is how many pound force per foot or newton per meter. So if I multiplied this by little dx, a little length, doesn't that give me a little df, a little force downward? Yeah. Look at the units, right? It wouldn't give me a little length times a little weight or newtons per length. That would give me a weight or a force downward. And so if I was interested in the total downward force, wouldn't I just sum up all the small contributions? What I'm trying to do here is review to help you bridge the gap between the calculus class that you mastered and then the application or the use of that calculus class, which is here in statics. Because if we build up that bridge, then you won't get lost as you proceed through the engineering curriculum. You'll be equipped at, oh yeah, I know what I'm doing here mathematically. So you would integrate over all the forces. Well, all the forces, well, we would sum over w dx, replacing df by w dx. And then we would integrate over the whole beam, going from location x to 0 to location b. So this gives us the equation for f of r. What is that net resultant force downward? Okay, so this is the integral, like I like to say, that you wish you would have had on your calculus exam, but you never were given on your calculus exam because it's too simple. But often engineering is that simple. So for this problem, is W a function of x, or is the intensity a constant? It's a constant. All right, can I take a constant outside of the integral? That's why I like this integral. And so I will do this. I'll say W times the integral of 1 dx. They never asked you that on the final in Cal 2, did they? I can do that. It's just x evaluated at the lower limit, upper limit, lower limit, upper limit. So this is just W times B minus 0. So let's drop that. Guess what? You could have guessed that result. It's the area. Yeah, area. Right? Okay, hopefully I didn't lose anybody. Hopefully you're all with me, because we're going to move to a triangular distribution. We're going to do the same thing, exactly the same thing. But now somebody says this was the sum of the forces downward. That's the criteria. That single resultant force has to have the same net downward force on the system as the distributed load. Well, what about the sum of the moments about a particular point? Let's pick point O, the origin. That's convenient. So you say to yourself, I'm going to have this simple system, which is just one force at a particular location, and this is my original system, and they need to have the same tendency to make that beam want to rotate about point O. Okay, so in the original system, how do I calculate it? Well, I would say every little downward force is at a location X away from the location 0, the origin, so I would sum them up, do the integration. That would give me the net moment of that distributed loading on the beam, the net moment around point O. Okay, we'll just expand dF like we did before. That's equal to W times dx. Might as well put the x right there. It really doesn't matter which place you put it, but the x is right there coming down. All right? And then we integrate from 0 to b. What does that equation represent again? It represents the moment of that distributed load about the point O. That's what it represents. And we want this to match the simple system. What is the simple system? One point force at a particular location. And that simple system is just the magnitude of F of R. We just calculated that before. And the proper location of where you should put it. We're going to derive B over 2. You're saying it's obvious, it should be right in the middle. Okay, but the math, trust the math, it'll show it. It's what it needs to be, B over 2. So what you do is you have the F of R times X bar. I need to scoot down. I don't like to scoot down, but I need to. Is this W intensity still a constant? Comes outside the integral. This is another integral they never gave you in Cal 2 final exam. What is the integral of x dx? 1/2 x squared, evaluated, the lower limit, the upper limit. And this F of R I'm going to replace with W times B times X bar. I need to scoot down a little more, sorry. So this becomes W 1/2 B squared. What about the other side? WB X bar. So let's cancel the W's. Let's cancel one of the B's. And we're left with the result that we anticipated that we would get, that the proper location is equal to 1/2 B. Bingo. If you understood that for a rectangular distributed load, it's easy to do it for the next one, which is a triangular distributed load. You ready to move to the triangular? Okay, let's do that. Now that I have a triangular distributed load, what do you mean triangular? Well, it's got a peak here and it's linearly related. As it goes down, it goes to 0 out to B. That's what I mean. Okay. Let's do this. Let's use our intuition. Let's use our intuition and say, I think, without doing any calculus, that F of R is equal to something. And most of you would guess it correctly. What again was it if it was if it was a rectangular load? It would be that magnitude of the intensity over the entire beam. It would be here, I'm showing H as the magnitude of the intensity times the entire beam B length. But that would be for a rectangular load. But can you tell it's kind of like this is the top, this is the bottom? Doesn't the triangle, isn't that just half of the area? So how do I modify? 1/2. 1/2 base times height. That rolls off your tongue. You did a lot of that maybe, before in some classes. 1/2 base times height is the area of a triangle. Just like that base times height was the area of the rectangle, as somebody already pointed out. Okay. Then the next question is, once I understand that, my guess or intuition says that. Where would I apply x bar? Would I apply x bar at b over 2? Would that be the appropriate location? No, it's too far to the right, isn't it? Shouldn't it be closer to the origin? All right, so now we just play a guessing game. We say, okay, maybe it should be 1/3 of b. No, 1/4 of b. Okay, 1/5 of b. So how close does it get? Where do I put it? It's not a half. That's too far over. And some of you know the answer. So what fraction is it? Is it 1/3 of b, 1/4 of b, 1/5 of b? 1/3, exactly. Now let's find it by calculus. Let's do the math. Okay, so we go back and we say, I'm considering the net force, the downward force, it's just like this, downward, F-O-R-C-E. And we have our simple system, and we have our original distributed system. They have to be the same net downward force on the top of the beam. Okay. The simple system is just F of R by itself. And the original systems is distributed load. But in this case, does the intensity change as a function of x? And this is probably the hardest part. And I've done this enough times to ask students, and this is what I want you to do. I'm going to take a break. I want you to give me W as a function of x. And somebody says, oh, I think it's going to be y is equal to mx plus b, where that's the slope and that's the y-intercept. Great, that'll work. But can you give me the equation? Because I think you need to get some of this. Okay, so I'm going to pause. I'm going to walk around when I get 5 people that can write the equation down. The intensity is a function of x. Notice that when I put in the intensity at 0, what should I get back from my equation? H. When I put in the equation x is equal to b, what should I get back out of my equation? 0. It's a straight line. All right, so a lot of you were able to get this W as a function of x, and that's not W times x, it's emphasizing, oh, W is a function of x, okay, is equal to negative the slope, because the slope is negative, so we'll put the rise over run, h over b, times x, and then the y-intercept was h. Most of you wrote that, right? Is that good? Okay. Now, do me a favor. You come over here and you say, the original system is distributed. The same little discussion, well, what is df? df is w dx, and then I need to sum over all the little df's, so I need to integrate over the length. I need to integrate w dx. Now that we have an expression for w, last time w was a constant, we took it outside. Not this time. Sorry, life is getting a little more complex. So now we substitute what w is, negative h over b x plus h. Did I do that correct? And we integrate from 0 to b. So we have negative h over b 1/2 x squared plus h times x, all of that evaluated 0 to b. So it's going to have negative h over b 1/2 b squared plus hb minus 0. So this is going to be, I cancel one of the b's, and we have 1/2 hb, negative 1/2 hb plus 1 times hb. Isn't that 1/2 h times b? Hey, is that what we set out to show? Yeah, that's what we set out to show. Okay, now that we did that one, that was all considering force. What's our next one? We say, well, our equivalent system needs to have the same moment about point O as our original system. Our simple system's moment about point O, maybe I can fit it in over here. I'll try and do that. The original, the simple system, that's just f of r, and I calculated the magnitude already, at the particular location x bar. And we already talked about that it needs to be something like right here, 1/3 over from the base where it's the height all the way out to the tip where it goes to 0, right? This should be that location, x bar, and we already got the magnitude. Okay, so we're looking to calculate this equation for x bar, finding its 1/3 base. Okay, is equal to the same moment that the original distributed system contributes about 0.0. Well, what is that? It would be the integral of the little moment arm distances times the little forces, but the little forces are the intensity times dx. And we integrate from 0 to b. Okay, so now we're back to here. So we have to do the integral from 0 to b of x times, and what was our equation for the intensity as a function of x? Negative h over b x plus x, or h. Okay, times dx. Probably since you wanted me to do this integral, you'll probably want me to do that one too, huh? Yeah, why not, Professor? You're on a roll. Go for it. Go for it. All right, well, fine. So this would be negative h over b 1/3 x cubed plus h 1/2 x squared, all evaluated, that whole thing evaluated 0 to b. I pause and I look at that. Am I on, or did I make a mistake? I have a mistake? Which is it? Well, I have an x here times this x, so I have x squared, and then I integrate x squared, it's 1/3 x cubed. Is that okay now? Okay. So thumbs up if you agree. You did it in your mind, and it looks good. There's a bunch of thumbs up. That's good. Very good. I'll move on. I'll assume that's correct then. Let's do this. So we evaluate at b, so this is going to be minus h over b 1/3 b cubed plus h over 2 b squared. Well, this b makes it a b squared there. And now I have 1/2 minus 1/3. What is that? What is 1/2 minus 1/3 times hb squared? 1/2, that's 3. I convert them all to 6, so that's 3/6 minus 2/6. Is that 1/6 hb squared? You agree? You agree? I promise I'll probably not to point at anybody. Sorry if I do. It's a habit, right? Do you agree? Give me a thumbs up if you like that. Okay, so let's bring down what we had on our right-hand side, our left-hand side. F of r was 1/2 hb, and then we had the x bar. So we have the 1/2 hb x bar. I'm finally ready to solve for x bar. X bar is bring that 1/2 over hb to the other side, or just do this, cancel the h, cancel one of the b's. I should have done it like that, there. And then we're going to have 2/6 of b. Well, 2/6 is 1/3 of b. Just like the math confirmed what we anticipated. Yes? This would be a problem that would be fair game on the exam, and it would have a rectangular component with a triangular component. Does that make sense? Thank you. And now one other point that I need to make. I'm going to insert a new page right here. Somebody says, I get a load that looks like this. It's a high right here. It goes down. It's linear. But it doesn't go to 0. It just stops, right? And so as a function here, maybe they say the intensity right here is, I don't know, 50 pounds per foot. And the intensity right here is, I don't know, 35 pounds per foot. And it goes from 0 to 3 foot in the x. See that? So they're plotting intensity, W, on the y-axis. And you have this shape like this. you have all the tools to solve this problem. And since I beat you up a little bit, how would you approach this problem? Do you see?
I would split it up into a triangle.
Right there. Right there. That's perfect. So what you do is you say, I see this. Don't go with the calculus. Don't try. You can do that and confirm that you'll get the right answer. But in the interest of time and being less error prone, or just do it this way. You have a triangle on top of a rectangle. And so what you would do is you say, I'm going to replace it by a point load representing the rectangle, and I'm going to put that at 1.5 right in the middle. And I could tell you the magnitude of that is going to be what? 3 times 35. I should have picked some easier numbers. Luckily, there's calculators. No. What is that? 3 times 35. 105? Yeah. So it's going to be a magnitude F. I'm going to call R1 because this would be the load 1, the rectangular part, and that's 115 pounds. And then I'm going to also put FR2. What's the magnitude of FR2? It's for the triangle, isn't it? It's a triangular combination. And so, oh boy, I should have picked some easier numbers. What is that? 15? 50 minus 35 is 15. So what's 1/2 of 15 times 3? 45 divided by 22.5. Thank you very much. You saved me. All right, so this is 22.5 pounds. And where should it be located? At 1. See? And then what you can do, so you take it and solve first this step, and then the last step would be, okay, I want to combine those into a single f of r. What would be the single f of r? What would be its magnitude? I would add the 115 and 22.5, so that would be 133.5 pounds. True? Oh, this is 105. You fixed it, huh? I'm going to pause. Is this okay? Give me a thumbs up if you're there. Thank you for that. Now, where do I place it? At the X bar. Yeah, where do I place that? You would just do the math. Basically, you're saying the same criteria that X bar times F of R, the single resultant, is equal to the original system or modified, which is 2 point loads. The first point load, FR1, at its moment arm, about the origin, of 1.5, plus FR2 for its moment arm, about the origin 1. Here we go ahead and substitute our numbers 105. And this one was 22.5. And then this one, after my errors have been fixed, 127.5. And now you can actually calculate what that X bar needs to be. And you can calculate it. Here's a little hint for those, as an engineer, you want to catch your errors before they become big errors, okay? And you want to be able to learn how to check your work. If somebody came along and said, I've calculated X bar to be 0.75 foot for this problem. What can you observe about 0.75 compared to 1 and 1.5? It's below the lowest. It's wrong. I can tell you, it's just wrong. All right, somebody comes in and they say it's 1.75 is X bar. It's wrong. I don't have to do any more math. I can tell you it's just wrong, right? Guess what X bar has to be between? The 1 and the 1.5. It'll always be, every day. Here's another thing you can do, insert new page, is you can say, here's one system, and the load looks like this. It looks like that. What did I just try to show? An itty-bitty triangular load on top of a huge rectangular load. True? And then somebody else says, here's a different problem. It looks like this. Comes up a little bit there and goes like that. What did I just try and show there? It's a little bitty rectangular load and a huge triangular load on top of it, right? Okay, if we had the same where this was 3, 0 to 3, and 0 to 3, the location of the single resultant force for this case where it's almost all, it's not all triangular load, but it's almost all triangular load, is going to be really close to, 1.0, sorry, you're right. And then this one, was it going to be very close to? If it's almost all rectangular with just half. Yeah. So there you go. Good way to check yourself is to know, oh yeah, it's going to be between these two extremes. All right. Did somebody run this number just to close it out? What do we get? 41. Thank you. 1.41 feet. You have a beam here, and you're just interested in, don't pay attention to the cable. That's not asked for. It's just they say you replace the distributed loading by an equivalent resultant force and specify its location on the beam measured from the pin at C. The pin is right there at C. And so there's no dimension here, and the distributed load starts right there. All right. So we're going to be measuring. This is the proper location to put it in. All right. So I look at it, and I have a rectangular. It's 15 foot, and it has a magnitude of 800 pounds per foot. And so I multiply the 800 pounds per foot times the 15 foot, and I get F of R1. That would be, replacing it just for the rectangular load, 12,000 pounds. Now, how many people have been solving problems in mastering engineering as well as the textbook, and they know that the solution for these problems are in the back of the book? You solved a problem like this, and then you look back there, and they go 12 KIP. Have you seen it? A couple of you? Perfect. If you haven't, naughty, you should have been solving more problems, because it's in the book. So what is a KIP? 1,000 pounds. Where does it come from? Kind of a slang. It's not pure metric. It's not pure anything. It's just a slang. It says like kilo, Ki for the kilo, and then they put the P for the pound. Somebody in my other class, when I explained it, said, that's foolish. Why didn't they just put KP for kilo pound? Well, first of all, the kilo is more on the metric than on the, you know what I mean. I mean, it would be like tons. You know, oh, we divide that by 2,000. We call it a ton. Okay. Don't worry, it's called a kip. It's 1,000 pounds. If you want to re-express that like that, the book does it a number of times. We understand. Where is this explained in our textbook? Chapter 1, page 9. Look it up, top of page 9, chapter 1. You can find what a kip is defined as. I'm not making it up. Okay. Let's now press forward. Come over here. We're going to have a second one. This will be the FR2. Well, you're getting good at this. It has the same 15-foot length. It's triangular. It has the peak of 800. Guess what that comes in at? Half of it. Yeah. And so then the total resultant is the sum of those two. We haven't figured out where to place it yet, but we're going to come in at 18 kip. Now, you could place the F of R1 right here. That's the best place to place it. If I started measuring X all the way over here, wouldn't that be at 7.5 for, this would be like X bar 1? And then how about for X bar 2? Let me pause, because I don't want you to make an error here. You're going to call it out, aren't you? I want you to give me X bar 2, but please let me walk around and get 5 correct answers before we move on. Why? Because I don't want to grade any exams with silly errors. All right. Why did I pause right there? I've graded enough exams, and I would have thought that somebody would come by and they would say, oh, that's 1/3 of 15. That's 5 foot. And they would use that in the calculation. But what does that x represent? It's the location from point C over. So it's not 5 foot, is it? I have to add the 15 plus the 1/3 of 15, which then comes in at 20 foot. Okay, I didn't do that to embarrass anybody. I'm doing that to save me time when I grade your exams. Because I can grade exams if they're perfect. I just say, check. Congratulations, I'm really happy. If there's errors, it's like, how much partial credit do I give them? Right? I got to try and figure out, where did they go wrong? How much did they actually know? How close did they get? Have pity on me. Make no errors. Okay. So there you go. Now what we do is we come in and we want to, we have those two locations now. I now have to read this problem. Did they say find where you specify its location on the beam measured from point C? Sure. So what we're going to do is we're going to have one single resultant force, and it'll be having that magnitude of 18 kip, and it needs to be at a x bar for the whole thing. Where do I find that x bar? Yep. Yep, do a moment calculation balance. So you have, again, what I like to think is the original system must have the same moment around point C as the simple system. The simple system just is f of r, the 18 kip, times that perfect location where that 18 kip should be placed. The original system, I know I moved from distributed to 2-point loads, but the 2-point loads have f of r1 times x bar 1 plus f of r2 times x bar 2. Hence, this equation for x bar is just going to be, let's do this one. That's f of r1 is 12 kip times the 7.5 foot. I should have put foot on that, shouldn't I? Plus, and I'm going to run out of room. I hate that. Okay, plus the 6 kip times the 20 foot divided by the 18 kip. And I know the units can be cumbersome, but I want to show that they do cancel. And you're left with foot as the right answer. And what does the answer come in at? I can't remember. 11.7 foot. 3 significant digits. Something with the equal sign in the box. Something to the left, something to the right, and don't forget your units. Right? Right? Makes sense? All right. So that was a good problem. Any questions on that? Ready to press on?